So this problem, we have this concentric pipes. Their cross section looks like this, and this red part is where the blood is flowing. So we have this small artery with a catheter inside in the middle, and the outside is where the blood is flowing, as you can see over here, just on this side. And you can see the velocity profile will look something like that. And we have central axis over here. So, as usual, in order to solve our Navier Stokes problem, we need to ask two questions to choose the right governing equation. What kind of coordinate system they use, and two, what is the direction of the flow? So among our rectangular and cylindrical coordinate, we know that this is a cylindrical coordinate because this is this round pipe, and we're going to use a radius. Radius as our radius, theta, and z as our coordinate rather than x, y, z. So among this rectangular and cylindrical, we're going to choose cylindrical coordinates, b. And among this, we have to ask the second question: what is the direction of the flow? Is it a vr, or is it v theta, or is it vz? We see that the flow is heading into z direction, so we know that we are choosing vz. So hence this third equation. So I wrote down this vz governing equation right over here, and as usual, our left side will all cancel out because this is steady state, so time doesn't really matter over here, and all the others go away because it's like one directional and fully developed. Now, on the right side, this is what's really important. First one, Vz over dr. So is the velocity on z direction changes as the r changes. So we can see that as the velocity changes, Vz changes over when it depends on the r, the location of the r. So we're going to keep this. Second one, does it change by the theta? So does that mean if you're looking from over here, depends on where it's at, or whether it is here or here, despite being in the same r coordinate, will the velocity change? No. So it won't. And Vz, well, this is a fully developed flow, so even if the location are here and here, even as long as the r is same, the velocity won't change. So it also goes to 0. And dp over dc, is there a pressure difference? Well, yes, because this is a pressure driven flow, and pressure goes from high to low, and that's how this flow goes. Because we need some sort of force to push this fluid to flow, and there's no gravitational effect, so we're removing that as well. So what we have left is this left side is 0, and mu is the viscosity, and all this minus dp dz. Afterward, we're going to move the dp dz to the left, and we have that. We're going to move mu to the left, so we have 1 over mu. And then we have 1 over r, so we're going to multiply by r on both sides. Well, we have r, and then we get rid of this 1 over r. And then we're going to take integral on both sides. So this, and 1 over mu is constant, and dp over dz is also constant. So after we take integral, we'll have r squared, and we have 1 over 2 over here, and then plus c1, and then we have just whatever that was inside here. And there's r here. So we're going to divide it by r. Because why we are doing this is we're ultimately just shooting for, we want just this vz term, solve respective vz. So vz equals something. So that's where we are heading to. Anyway, so divided by r, so this just becomes regular r from r squared, and this will have c1 over r. And we take integral, then we'll have r squared again, and 1 over 2 times 1 over 2, so we get 4 over here. C1 ln r because it was C1 over r, and C2. And this is what we have ultimately. And now we need to solve for C1 and C2. And in order to solve it, we need to use the boundary conditions. Most of the cases, we only have 2 conditions we can use, and here we have actually 3. The first 2 is that we know the velocity at this Ri, at this very wall, and at the Ro, the velocity of the fluid will be 0, because it's a no-slip wall, and that's how it is. Second is, we know at this very point, when the velocity is the highest, we know that the dvz over dr, will be 0. So derivative will be 0. The change in velocity will be 0. And how do we define that? Well, we know, so we want to know the location of here when the speed is the highest, which is the very center. So in order to get just this area, well, we can say the length of here will be RO minus RI, and that is the length, right? And the half of that is where the velocity is the highest. So RO minus RI, and that is to represent just this length. But if you were to just use that as R, then it's going to fall under somewhere here, because this is where R0 is. So we need to add Ri to it. And that will accurately represent the location where the velocity is the highest. And we can even further simplify it by saying, well, because 2Ri over 2 is same as 1, just regular Ri, right? And if we add them up, we'll have Ro plus Ri over 2. So we're going to write Ro plus Ri over 2. And that will be where the location, that's the location where the velocity is highest. And we know dv over dr, the change in velocity, will be 0. And I'm just going to random choose this one and this one as our boundary conditions. I just need 2 equations because C1 and C2, we only have 2 unknowns. So when velocity when R is equal to Ri is 0 at the wall. And I'm just plugging in Ri on this equation. And then for the second one, dv over dr, which is just here, when Ro plus Ri over 2, R is equal to Ro plus Ri over 2, it's going to be equal to 0. And just plug and chug over here. And if you solve for C1, you're going to get something like that. And it simplifies to here. In C2, just plugging back into over here. Now that we know C1, we can plug, and I just solve for C2. So we can put this in and get C1. I won't actually do the thing because it will take longer for me to do the job, but it's pretty intuitive. It's easy afterward. And that's how we get velocity profile equation. Then how can we get Q dot, which is a flow rate? Well, as you probably know, Q dot is V average times cross-section area. And this equation makes sense. It's because the unit of velocity is meter per square, right? How many meters does it go in a second? How fast does it go? So that's the velocity. And that cross-section area's unit is meter squared. And applying that, we get meter cube over second. That's for Q dot. And that shows how much volume does it go through in a second. So this represents our volumetric flow rate of Q dot. But we can't just use this equation because we don't know the V average. As you know, we have cross-section here. the far at the very center, the velocity is highest, and as we approach the wall in both directions, it slows down. So what we need to do is use calculus to solve it out. So V is represented as VR, and this cross-section area actually represents only this thin like a donut thin area where it's so small that the thickness is dr of this ring, and this length, if you stretch it out, it's going to be 2 pi r because of the yeah, it's 2 pi r length. So this represents our velocity, this represents our area. Okay, infinite amount of number of this ring that we're going to use to calculate. And the boundary will be Ri at here, because we're not going from the 0. So from Ri to Ro. And we just use the velocity profile equation that we got over here, and then put 2 pi r dr and solve the integral. And you'll be able to get q dot. And what if we were given to solve for shear stress at certain location? Well, shear stress is defined as viscosity times shear rate. And shear rate is just the dV over dz in our case. Change in velocity over change in distance. So we can plug this back into our original equation, and we get shear stress is equal to viscosity times dV over dz. And we have dV over dz from our previous page, right over here. And we solved for C1, so we should be able to solve for shear stress at a certain location by doing mu times whatever you got in the previous page. And let's say if you were given to solve for a velocity average, you can also solve for velocity average because we solve for q dot, we can just do q dot divided by cross-section area and get velocity average as well.